be studying a very important technique of logistic regression, which is a part of a GLM family, which is used everywhere in classification problems. So we'll be studying logistic regression through a breast cancer classification problem of a breast mass obtained from a biopsy of breast cancer patients. So basically, it's based on an image of the normal and the malignant tumors. To start off with, I will again load the data using pandas. And again, I will load all the usual libraries such as pyplot, numpy, and I will read the data using read CSV function for pandas, because again it's a small file, we can easily load it directly into memory. And then I will add the column names and then use the head function to print the top 10 rows of this particular data set. So this is the data set, and as you can see that it has a lot of columns, and all of these columns are basically based on the characteristics of that particular image. So we have IDs, for example, these must be the IDs of the cases we have identified, and diagnosis is basically a classification problem. And then you have the radius mean, the radius standard error, radius worst. These are all based on that particular image of the breast cancer tumor. So continuing on, what I will do is I will use again the functions from sklearn library, such as pre-processing. This is simply to convert the categorical variable, which is our target variable, which is this particular column diagnosis, into a numerical variable. So simply speaking, labor encoder will simply convert M and B, which is malignant and benign, into the numerical equivalent. So then we will use the transform function to make the change here. And then moving on, we'll calculate the correlation matrix for this particular data set. And then we will store it in this variable core mat. And we will store the values of this matrix and then sort them using sort values. So we'll get the highest to lowest. Next up, I will do something very simple but useful. Let us take the difference of mean values of each of the columns for malignant and benign labels, and I will find the difference between the mean of each of the columns. So to give you an example, for example, if I have compactness mean, I will take the column compactness mean, and I will take this for the benign column, where the label is B, and M, where the label is M. I will calculate the mean of these two vectors. So I will calculate the mean of this, and I will calculate the mean of this, and then I will calculate the difference between these two values. So this minus this, and then I will store it in here. So the idea is that, simply speaking, the variable which will have the most difference will be useful for us when we are creating our classification model. I'll start with the describe function. I will take this output, this particular column called mean of the pandas describe function, and we find this mean for each of these vectors or columns or features for the data set, and then we will find it for benign, and we'll find it for malignant, and all these other variables or values for all of these or features. Standardize this particular metric or statistic. So here, for example, I have taken the mean of benign and malignant tumors. Then I'm going to standardize this mean using the relationship of x minus minimum value and divide by maximum minus minimum, right? So this will convert everything in the range between -1 and 1. And then simply I will take the difference, absolute difference between the malignant and the benign diagnosis, and then I will sort the values. So in effect, I will have those columns or features which have the maximum difference in means between tumors. So continuing on that, we can see that the output is sorted from very low values for compactness mean, standard error versus compactness worst. Texture mean and concave point worst have the higher difference between these two populations. So this suggests that these variables might be important for us later on when we will be building our model. So now that we have found the mean value difference between the two populations, let us create a data frame which will store the values of correlation and difference in mean, which we calculated earlier. So as you have seen earlier, we calculate the correlation of each of these features with the encoded value of diagnosis, which was done here. And then obviously we sorted those values. So the features with the highest correlation will come first. And having done that, I have created a data frame to hold these two metrics, and then I'm just going to plot these two vectors for that is the correlation of each of the features with the target variable and the difference of means, and try to see which of these variables will have the highest impact on the response or the target variable. And this is just simply what we call as feature engineering. We are trying to find which features have the most impact on the target output. And we see that some of the features, for example, fractal dimension mean and concave point standard error have a higher correlation than compared to other features. And similarly for difference of means, we see that radius worst and concave points worst have a higher difference. So these two will form more or less the basis which we will look at when we are going to create our models for classification. And then we can check whether our data set is balanced or not. Now for a dichotomous variable like this one, where we have two choices, malignant and benign, we want the target to be equally represented in the data. So that means that if we have more benign than malignant, it will be an unbalanced data set, and which it can potentially impact our final classification model. So simple check can be done to see what percentage of values are benign and what are malignant, and we see that it's around 59%. So for a perfectly balanced data set, this would be 1, because the ratio of the two factors, or the ratio of two variables, target variables, malignant and benign, will be equal. So this is a slightly unbalanced data set. That doesn't necessarily mean the model will be inaccurate, but the model can certainly be improved by collecting more data. So you can also check for missing values. For example, there are no missing values in this particular data set, but generally there are in practical applications some missing values, and we can use several imputation techniques to tackle that problem. Now let us move and look at these two classes visually. So I'll take an example of concave point worst feature. So I will start my visual exploration and I will create distribution curves of this particular feature. So in this case, we see a more or less clear distinction between the two classes. And again, this is a simple histogram for concave point burst, which I've created using plt.hist, which is a standard function of the PLT or pyplot library, and then we will add the rest of the plotting details such as labels, titles, and legend. And you can also specify the bins or the intervals. In this case, I have put them to be 100. You can see a clear distinction between these two classes, and what that means is that we probably won't require to do a transformation such as using what is called as the kernel trick. So basically we take the dimension, so we take the vectors or factors into higher dimensions and try to find separability. So taking the next example, we have fractal dimension mean. And again, we'll do the same functions. We'll do hist, then we will do label, title, and legend. And again, we'll take the two classes, malignant and benign. And we'll see again that there is again a clear separability. So the mean of this particular histogram will probably be around this point. And then for this particular curve, it will be around maybe this point. So there is a difference we can see, which will be important later on when we are trying to model different for these two classes. And similarly, I can also do the same visual exercise for radius mean. And again, we will see a clear separability, although there is significant overlap in this case. So as part of our observation, we can see that based on simply visual exploration of these three variables, we can see that the blue malignant tumors or class have a higher units than compared to the benign tumors or class based on these three variables: radius mean, smoothness histogram, and the concave points burst, fractal dimension mean, and radius mean. So let's move on to another analysis for correlation and also correlation heat map. And this analysis is required because we want to more or less check for multi-collinearity between different factors or different vectors or features which will impact our final output or response or target. Because logistic regression is part of a GLM family, GLM models typically work well when the multi-collinearity is minimized, means that the correlation between the classes is minimum or zero. So a good way to check that visually, it's just create something called as a heat map, which is a visual representation of correlation between values or vectors. So you can see there's a scale, there's a color grading going from dark blue till dark red, and points which occur at about 0 have a lighter curve. So we typically we want all of this to be at around 0 or have a lighter shade. So darker shade regions represent some sort of a correlation between individual features. For example, this part here, and so on. So to perform this particular operation, what I've done is I've scaled the features first using standard scaler, which is provided out of the box by sklearn pre-processing function or module. And then we have a package called sklearn pandas, from which we will take the object called data frame mapper. Now, data frame mapper simply provides additional features and further adds to the existing pandas and sklearn toolkit. So data frame mapper is just a function which is used in feature engineering, and it allows us to apply column functions or apply functions easily to all columns using sklearn API. And here I'm simply in the first line, I'm simply using the standard scaler, and I'm returning a tuple using this list comprehension statement. And then I'm returning n, which is the index of the column, and then the scale value using standard scaler. And then I'm putting that in this data frame mapper object, so that it will apply this fit function to all the values, all the columns of the dataset. And then finally, we will use the transform function like we saw earlier to transform the scaled object onto the data frame. And then finally, we will take the correlation using CORR function or the correlation metric as provided by the data frames object. And then finally, we will use seaborne heat map visual function to create this particular heat map, and then we will add the tick labels using setX tick labels, which will give us the labels for these y and x values. So this was a simple visual inspection for multicollinearity among the features. And what we observe from this particular exercise is that there is some multicollinearity in between features. Doesn't necessarily mean that it will impact our model significantly, but if in a later experiment we can repeat the sampling process without these features, probably it will produce a better model. So let us continue on and start creating our initial model. Let us begin the modeling process here, and first I will again import the stats model formula API, and I will take the logit function from this particular module, and then I will also import the standard scaler and the stats model API as SM, and I will create a copy of my data set for modeling called df-full, separate out the test and the training data sets using pandas ilog indexing function. So basically I will take 80% of the rows into train and then 20% of rows into test. So as you can see here, the first 80% of the rows will go to train and the last 20% will go to test. So having done that, then I will select the first 20 features based on the highest correlation which we saw earlier in that particular visualization. And then I'll convert the feature names into a string list for appending into a formula string. And then we will use the logit function which takes in this particular formula string and the training data set or training pandas data frame object, and then use the fit function like we did earlier. And then finally we will use model.summary to produce this output. So summary provides us a very comprehensive model details, including coefficients, model performance indicators, etc. Now let us look at some of these values, and let's start with the pseudo R squared. So pseudo R squared is basically an analog or a comparative metric to linear regression R squared metric, which is used to evaluate the models. But basically, instead of measuring residuals, squares versus total squares like we do in linear regression, pseudo R squared works on the ratio of likelihoods. And what it does is it simply compares the model with random chance. So, for example, if we are to write it, like be 1 minus uh, the likelihood of model with all its features and then null likelihood or only with the intercept term. So if you get a value of 0, that means our model does equal to or worse than the um, than the random chance then as compared to random chance. And then we can look at the log likelihood metric. So the higher it is, the better. And then this is the p-value of the LLR or likelihood. And LLR test is actually the counterpart of the F test, which we do in linear regression. So again, p-value, which is significant, simply tells us that our model is significant um, and is better than simple chance. So then you have the coefficient values of each of the factors, you have the p-values, and you have the confidence intervals of each of these factors or features. And let us look at the final accuracy output of this particular model. And to do that, I will use the predict function on the model as provided by stats model object. And then I will simply use the accuracy and the confusion metrics from sklearn metrics functions. And I will create the confusion metrics using our prediction and the actual test values. So this is my confusion metrics and this is my test accuracy. It's high, it's about 94%, and my confusion metrics is also good. It's about positive of about 6 and false negative of about 1. So the model is doing pretty well as compared to these metrics. But let us see whether we can improve our model, and not only improve our model but make it more simpler and improve the explainability of this particular model. Now again, this will depend on the application we are involved in, but let's say we are studying breast cancer, so we want to understand which factors most impact the discovery of malignant versus benign tumors. And we have a lot of features here, starting from dimensional, fractal dimensional mean up till compactness verse. But let's see whether we can try to simplify it within 2 or 3 variables. So what I will do here is I will do a little exercise here, which is simply sorting out the features or the vectors in terms of their coefficients. So the idea here is that we have our GLM or logistic regression object. So for example, we will have our logit of y, which is simply y log of natural log of y over 1 minus y equals to our linear relationship of the different features. So for example, it will be beta naught plus beta 1 x plus beta 2 x1 x2 and so on. So what I intend to do with this particular script is just label is just sort out the values of betas for a standardized x's. So for example, all of the x's are between -1 and 1, and I just want to label or to rank betas in terms of their coefficients. And again, this is very simple, but this is very useful because we can take the ones with the highest of coefficients and then create a model and see whether we can reach the accuracy of our previous full model using a fraction of features. So let's see how that works. So again, this script, in this case, I'm using sklearn model because sklearn provides a lot of functions out of the box to do this operation. And then we will take and then we will fit the model again on train, x train and y train, which is the training data set, and y are the target or the labels, and then we will take the coefficients and then we will simply rank them from highest value to the lowest value using this particular operation of dictionary list comprehension. So this will be our output. So you can see that we have the lowest for parameter worst and the highest for the standard error. I will repeat the modeling process. I will create a smaller model like we discussed with only a few features. So I will select, for example, the smoothness random standard error, which is here. I will select concave standard error, which is here. So what I'm doing is I'm taking the values or the coefficients with a higher value and I'm putting it in my model. Now you can repeat this exercise. It's using the same procedure for creating a model. We are taking our data set. We are taking only the columns we are interested in. As is the norm, we are creating the test and the train data sets. And then we are creating our formula, which is required for the stats model modeling framework. And then we are using the fit function and the summary to print out the results. So it's the same procedure, but you can experiment and change the values or change the columns and see what output that you can get. But overall, our objective will be to explain or to understand discernibility or the difference between the two classes of B and M using as few features as possible so that we can explain more clearly which features have the most impact. And you can also use an experimental technique called RFE or recursive feature engineering, which is again provided out of the box by sklearn. And what it does is it will do a stepwise learning approach. So for example, it will take one feature at a time and see whether the output or the target, for example, accuracy, log likelihood, etc., whatever we set, improves or reduces its own. And then it will take the features which have the most impact on the improvement of our selected metric. But here I have taken a very simple approach and simply taken the coefficient of our model. And to check the final accuracy, I again repeat my process and I get a figure of around 94%. And my confusion matrix is also roughly the same. So it seems that these features are one of the most important ones which have the impact on our model, which impacts the most on the classification of our breast cancer image results. And to further improve our model, we can minimize overfitting in these models. And overfitting is a concept used in analytics or data science, which occurs when a model or function fits exactly against its training data. These models, in fact, memorize or encode the properties of the dataset including noise or variance, and do not perform well on the test or unseen data. When this happens, the algorithm cannot generalize and is thus ineffective as a model. And regularization plays an essential role in preventing data from overfitting by adding additional terms. What happens is that these terms penalize the overall model when there is regularization. Instead of learning, these terms will penalize the overall model. And to think about it very simply, for example, if we have our model, let's say I will take an example of a very simple model. So we have alpha plus beta 1 x1 plus beta 2 x2, and let's say that due to memorization on a particular data set, the value of beta 1 becomes very high. So this is very high and this is very low. So what the regularization term does is, for example, if you can add regularization, it will be simply a function which will take these two parameters of beta 1 and beta 2, beta 1, beta 2, and this function will ensure that the values of these two coefficients are balanced, such as one do not disproportionately increase as compared to other. So if you want to think of in another way, you can say that, for example, if you have a function y equals to x squared, and it is sort of like a curve, right? It's at origin it's 0 0, and then it increases across both sides of the x-axis. Now if you add a term in it, let's say minus x, this will prevent it from increasing too much. So for example, at x equals to 6, this function will be 30 and not 36, right? So the concept is same. Regularization tries to even out all of these coefficients. And there are two kinds of regularization terms, mainly one is L1 and L2. And L1 is basically associated with the absolute function, and L2 is associated with the square function. And L2 is actually much more computationally feasible and is used much more as compared to L1, but L1 is more suitable for sparse data sets. So now moving on, again, these lines of code are very similar to the earlier examples which we have seen. We are again converting data into test and training sets. We are creating our formula for our model, and in this case I'm just using three features: fractal dimension, concavity worst, and concavity points mean. And here I'm shuffling data to avoid any sort of autocorrelation issues, and I'm using the logit function from stats model, and I'm using the regularization function plus the alpha, which will be the coefficient of regularization. And finally, like we have seen before, we'll use summary function to print out the output, and this will be the output. And again, we can see that we only had three features, so all of them have 0 p-values, so they are more or less very significant. And these are the coefficients, and these are the confidence intervals as provided by this particular package. So let's work on the accuracy and the confusion metrics of this particular model. And the accuracy has slightly increased to about 96.5%. And we can also calculate another metric called F1 score, which is used for classifiers and again provided by the sklearn metric. So this is around 0.96, and our confusion metrics also looks good. So to summarize what we have done so far, we have started with the complex problem of cancer mass classification based on biopsy image data. We analyzed features, we built our logistic regression model and further improved and simplified the model using regularization and some optimizations. And again, there is room for experiment. We can still experiment further and do some improvements, like for example, changing the hyperparameters, etc., checking multicollinearity, um, having more data for this particular problem, and so on. And we can also conduct further tests on these features which we discovered, such as fractal dimension, concavity, and the one we discovered having higher correlation with the target variable, and the ones with the higher coefficient values, for example, area, standard error, and so on. So these can be investigated further in, let's say, a follow-up study to determine which factors or factor is more significant as compared to others. So this was it for our logistic regression. That's it for this video.